Welcome, curious minds, to another deep dive. We're exploring the really fascinating world of the online encyclopedia of integer sequences, especially for you number theory students out there. These sequences, they're almost like hidden maps, aren't they? Pathways to some deep mathematical ideas.
They really are. Amazing structures.
Today we're looking at OEIS A000315. It counts something called reduced Latin squares. And it also connects to, well, algebraic structures labeled loops specifically.
Yeah, and what's fascinating, I think, is how you start with this simple-seeming grid arrangement. And it spirals into these really complex counting problems and, surprisingly, has quite diverse applications and even touches on deep properties of numbers.
Okay, let's back up a little for everyone. A Latin square, what exactly is that?
So imagine an n-by-n grid, like a checkerboard. You fill it with n different symbols, could be numbers, letters, whatever. The rule is each symbol has to appear exactly once in every single row
Okay.
and exactly once in every single column.
Ah, right. Like you mentioned, Euler used Latin characters, hence the name.
Precisely. Leonhard Euler, yeah.
So like the 3x3 grid, maybe with ABC. Each letter shows up just once per row, once per column. Got it.
Exactly that.
But this sequence, A000315, it counts reduced Latin squares. What makes a square reduced?
Right. A reduced square is a special case. It's one where the very first row and the very first column are in their natural order.
Natural order, you mean like 1, 2, 3, or ABC?
Yes, exactly. Just the standard sequence, 1, 2, 3, up to n.
Okay, so why do we care about reducing them? Is it just to make counting easier?
Pretty much. It's a way to standardize. You see, you can take any Latin square, and just by shuffling the rows and columns around, you can always transform it into one unique reduced form.
Ah, okay. So if I had 1 starting AC, B in the first column,
Yeah.
I could just swap the second and third rows to get A, B, C, and that would be the reduced version.
Exactly. It means we don't count squares that are fundamentally the same, just, rearranged as different entries. It cleans up the counting process.
Right, avoids duplicates. Makes sense. Now here's where I saw things get wild. The numbers themselves. A000315 starts simply. N1, it's 1. N2, it's 1. N3, also 1. Seems tame. But then N4, it jumps to 4. Angle 5 is 56. And NE6, you said it's 9,408.
9,408, yes. It grows incredibly fast, explosively almost.
Wow.
And counting these has historically been quite tricky. The records show several attempts, some with errors that needed correcting later on. It just highlights how hard this combinatorial problem actually is. There isn't a simple, plug and chug formula.
No easy formula.
Well, there's a known formula published back in '92, but it's highly complex, involves something called permanence of matrices, not something you'd calculate by hand easily.
Okay, so it's computationally demanding.
Right.
But you mentioned a connection to number theory earlier, something really fundamental for the students listening.
Ah, yes. This is quite beautiful, actually. A result by Stones and Wanless from 2010. They showed that an, the count for a given size n, has a fascinating property related to whether n is prime or composite.
Oh, how so?
If n is a composite number, like 4 or 6, then an is always divisible by n. It's 0 modulo n.
Okay, divisible by n if composite.
But if n is a prime number, like 3 or 5 or 7, then an is congruent to 1 modulo n. It leaves a remainder of 1 when divided by n.
Whoa, so the count itself tells you something about the primality of the size. That's really neat. It's like a hidden property.
It is a direct link between this combinatorial count and fundamental number theory. Quite profound.
So beyond the pure math, where does this stuff actually show up? Real-world applications?
Oh, definitely. Latin squares are surprisingly practical. R.A. Fisher, the famous statistician, used them extensively in designing agricultural experiments.
Agricultural? How?
Well, imagine testing different fertilizers on different plots of land. A Latin square design helps you arrange the tests so you can filter out variations in soil fertility across rows and columns. Ensures a fair comparison.
Clever. Okay, what else?
They are essentially the multiplication tables for algebraic structures called quasi-groups, which we mentioned briefly.
Right, the loops connection.
Yes. Quasi-groups are a bit like the groups you study in algebra, but slightly more general. Latin squares provide a concrete way to visualize them.
Okay. And puzzles.
Sudoku. A Sudoku puzzle is basically a specific type of Latin square with an extra constraint about the blocks.
Huh. Of course. I knew it felt familiar.
And there's more. If you have pairs of Latin squares that are orthogonal, another property, they become incredibly useful in coding theory for creating error-correcting codes. The kind used in communications, like ensuring data gets through reliably, even over noisy channels like, say, broadband over power lines.
Amazing. So from designing farm plots to abstract algebra to Sudoku to making sure my internet works, all from this one sequence. All 000315 and the squares, it counts.
It shows how these seemingly simple combinatorial objects can have really deep roots and far-reaching branches.
It really drives home that fundamental mathematical structures often hold this immense, sometimes hidden power and utility.
Absolutely. And it makes you wonder, doesn't it, what other mathematical objects are out there waiting for us to fully understand them? And what possibilities might they unlock?
A thought to ponder. Keep exploring those sequences, everyone. And join us next time for another deep dive.